Welcome to lecture 4.6. In this lecture, I'll be dealing with how to handle multiple substitutions on benzene and how we can add multiple groups in sequence to make fully elaborated, complicated benzene-based structures. To do this, let's first define what I mean by substitution when it comes to benzene. So far, we've been dealing with unsubstituted benzene. That is a benzene that has no groups on it to start. When that happens, we can put the electrophile that we add really wherever we want. All the positions would be equivalent. You could rotate that product to make the same thing. However, after this reaction, we now have a monosubstitute benzene. One of the hydrogens has been substituted for some sort of group. Of course, these are going to be the electrophiles in our EAS reactions. But now, what happens when I want to add a second electrophile? Where do I put it in relation to that first one? And even further, a disubstituted benzene. Now we have two different groups. If I want to add a third one, where would I put it? By the end of these next few videos, we'll be able to have really solid answers to these questions and understand mechanistically why we get the products we do. To delve a little deeper, let's quickly talk about naming these different benzene positions. So initially, as I mentioned, unsubstituted benzene has all the positions as equivalent. Where you add this first electrophile, whether it be a Friedel-Crafts alkylation, acylation, nitration, whatever it is, doesn't matter. However, once we want to add a second electrophile and we're producing a disubstituted benzene, now we actually have three distinct options. The electrophile can move to this position, or this position. As you can see, while very similar, these products are distinct, they're different. In the first reaction, or in the first product, we can say that we have these groups close together. Here they're further apart, and here they're as far apart as they can be. Let's define these with some names. Okay, so this original position is where the first electrophile was. The position that is closest on both sides is called the ortho position. Sometimes this original group is called 1, or numbered as 1, and this is the idea of we call this a parent group. The group that was there before. The ortho positions are one away from the original group, or they can be defined as the 2 position on both sides. Then further away, we have the meta position, and across from the original, across from the parent group, we have the para position. So now we have some understanding about what to call these, right? Here we could say that our first molecule was adding the electrophile to the ortho position. Here, electrophile 2 was added to the meta position, and here, electrophile 2 was added to the para position. One thing to be careful of is that ortho, meta, and para aren't objective positions on a benzene, right? Now that we have 2 electrophiles, they each have their own ortho and meta and para positions. Just for example, looking at this structure, from electrophile 1, this position is para, but for electrophile 2, this position is para. So it's in relative to the group that you're talking about, but when we're dealing with a monosubstituted benzene, of course, there's only one group to consider. We'll start with that, and then as we move on, we'll introduce how we can handle more than one group. Now that we know the names of these positions, let's talk about predicting what's called the ortho-meta-para selectivity. I'll just say OMP. How do we tell where that second group will go? A very important idea is that the group being added is irrelevant. Okay, going back to this overall equation, that means that what matters is the parent group, not the electrophile. Of course, we're adding the electrophile, but where it goes does not depend on what we're adding. It depends on what was there before. Right? So definitely focus on that original reactant. Only the parent groups of the reactant matter. That's the idea. We call these sometimes directing groups, as they direct the reactivity to a certain position or certain positions. There are 2 general types of directing group. The first is called ortho-para directing groups, as quite hopefully obviously, they will direct to the ortho and para positions. These will be the areas where you're going to see your substituents going. You won't see them happening on the meta position. So ortho-para directors are typically electron donating groups. As we've covered previously in aromaticity and conjugated systems, electron donating groups include things that have heteroatoms with lone pairs. We'll talk in the next video about how this works. I want to quickly mention that we have different strengths of electron donating group. Broadly, you can group them into two categories. Strong electron donating groups have that lone pair and can induct with resonance, as we talked about. But weak electron donating groups include alkyl groups. So these alkyl groups, really any carbon chain, these are going to still activate the ring, and we'll talk about what activate means in a bit, but they are not as strong as the ones that actually have lone pairs. Here's a list of what some of these activators may look like. Notice that for every activator, assume that the squiggly line means that it's directly connected to a benzene ring. Every single one here, whether it's an alcohol, an amine, primary or secondary amine in this case, an ether, even esters, when they're connected by their heteroatom here that have the lone pair, these are able to activate the ring, and they fit this idea of an electron donating group. They can all donate in. Let's look at an example of why this might matter when trying to design a disubstituted benzene compound. So, looking at this compound and trying to synthesize it from benzene, we see two groups need to be added. The first is a methyl group, and the second is an acetyl group. Now, obviously, we can use Friedel-Crafts alkylation to add a methyl group, and Friedel-Crafts acylation to add that acetyl group. However, as you're now going to discover, the order that you do this in does matter. Let's try the alkylation first. To do the Friedel-Crafts alkylation, we'll use methylbromine and FeBr3. Remember that without FeBr3 as a catalyst, this reaction will not go, and that will produce a methyl group. Now, I'll draw it where we want it, but again, there's no selectivity at this point. You can put it wherever you want. Now that we have this methyl benzene, also called toluene, we can try to add our acetyl group. To do that, we would add the carbons that we want with the bromine, right, the acyl group, the acyl bromide, and FeBr3 once again. Now, the idea is that when you have an electron donating group like the alkyl group, which is what we have in this example, it is an ortho para-directing group, which means that the subsequent groups that we're going to add, like this acetyl group, are going to be focused on those positions. That means that this pathway works. It is a valid pathway. Based on the parent group, the acetyl group is going to go where we want to, noticing that that is para to the methyl group. So what if we try the acylation first? Well, we'll use the same conditions. And here's what we get. We get the acetyl group, and we'll put it down here. The problem is, as we're about to talk about, this is actually a meta-directing group. This group is going to put the methyl group here instead, on the meta position relative. So when I try to do the alkylation, we are not actually going to get the product that we want. We're going to get a methyl group here instead, meaning that this is not going to work. Right? The reaction will work, but it won't make the selective product that we want. Hopefully this demonstrates why this topic is important. Not only do we need to know the reactions, but we also need to know the order of reactions that will get us the products that we want. As I mentioned, that group, the carbonyl, was a meta-directing group, so let's talk about them quickly. Meta-directing groups are typically the opposite. They're electron withdrawing groups. Again, we'll talk about this in the future videos to come as to exactly why that's the case. Generally, they're deactivators, and they are a substituent with a conjugated pi bond. We've seen this previously. So, for example, all of these will fit that rule of conjugated pi bond to a benzene ring. Right? Every single one won't be able to donate electrons with resonance, but they will be able to take these electrons out and withdraw from them. As you can see, the ketone, the aldehyde, interestingly, the ester and the amide show up here again, but notice that they're connected differently. Instead of being connected by their oxygen here, they're actually connected by the carbon of the carbonyl. So esters and amides can't be classified exactly as always activating or always deactivating. Right? It depends on the way that they're connected. I want to quickly touch on two different exceptions to this idea that it's a conjugated pi bond. We may see a trifluoro group, sometimes referred to as a triflic group. And these fluorines are just very electronegative atoms, so some of the most, probably the most electronegative atoms. And they're going to be pulling a lot of electrons, so despite not having this carbonyl, they're still absolutely electron withdrawing, and they are going to be meta-directing. Another interesting one to refer to is when you take the NH2 group, which again typically has a lone pair and is an ortho-para director, or an activator. When it's protonated in the presence of acid, it actually turns into NH3+ and no longer has that lone pair. If we think about what positive charges tend to do when they're near electrons, they're going to attract electrons toward them. So this group is also an electron withdrawing group. With that covered, let's quickly talk about an example. So here we can just do a quick example showing that now we have this group. We recognize that it has a carbonyl that's conjugated to the benzene. It's a deactivating group, meaning that the next reaction, whatever it is, it doesn't have to be the alkylation. Whatever the next EAS reaction is, will go to one of the meta positions. So we can redraw the original molecule here, and we can see that this is going to be the Friedel-Crafts alkylation since we have an alkyl halide in the presence of FeBr3, and we can add that group to either this meta position or, if we wanted to, this meta position. Excellent. So I've been using these terms activator and deactivator. Let's talk about them briefly. Recall that in EAS reactions, benzene isn't being attacked, it's doing the attacking. It is acting as a nucleophile that is attacking electrophiles. So thinking about what that group might do, if it is an electron donor group giving electrons to the ring, that's going to make this reaction better. It's going to give the benzene, which is normally pretty stable, more electrons than maybe it wants, which will convince it to attack more readily. On the flip side, if I was to put an electron withdrawing group, right, these typical meta-directors, on the benzene ring, that would reduce the reactivity of the ring. Indeed, some benzene rings, if you put enough deactivators or strong deactivators on them, they'll stop reacting in EAS entirely. So let's talk about the strength of these activators that I've mentioned. For the activators, these are your electron donating groups. Recall that if you have a lone pair directly, you're a strong activator. These are all, by the way, ortho-para directors. So oxygen, for example, or nitrogen there as aniline, these are your strong activators. The alkyl groups, as we talked about, are weaker activators, and this is basically a list of the reactivity of these different compounds. So benzene here is the least reactive. Now looking at the strong deactivators, one thing I want to point out is that the nitro group, NO2, is an exceptionally strong deactivator. Typically, if you add the nitro group first, you're not really going to be able to get this reaction to go further than that, or at least not easily. So these are both considered strong deactivators based on that fact that they have a pi bond to an oxygen connected directly. Right? They're both able to do this resonance. However, the nitro group is even stronger than the carbonyl. Of course, these are both less reactive than the original benzene. These are generally meta-directors, but as we'll talk about, there is an exception here. So now that we know about activators and deactivators and how to group them, as well as the directing properties that they have, we can move on and talk about the mechanism by which the electron withdrawing groups, such as these two molecules, are withdrawing and therefore meta-directors, and why the ortho-para groups are activating and ortho-para directing. I look forward to seeing you in the next video to discuss these topics.